Thank you, Jane. I'm very excited to introduce our next speaker, David Montgomery, a MacArthur Fellow and Professor of Geomorphology at the University of Washington. David is an internationally recognized geologist who studies landscape evolution and the effects of geological processes on ecological systems and human societies. An author of award-winning popular science books, he has been featured in documentary films, network and cable news, and on a variety of TV shows and radio programs as well, including Nova, PBS NewsHour, Fox and Friends, and All Things Considered. When not writing or doing geology, he plays in the band Big Dirt. This is what I want to hear more about. He lives in Seattle with his wife, Annie, and their black lab guide dog dropout, Loki. Let's hear it for David.
Can we take it all the way back?
Yep, I will. I'll get you from the beginning.
Great. Thank you. Well, I'm honored to be here to address this meeting, and I'm on West Coast time, so if I'm a little shaky at the start, it's not because I'm an academic from Seattle, it's because it's 4 a.m. But my job today, I think, is really to talk you through a journey that I've been on, because I'm a geologist, as was mentioned, by training. I trained as an undergrad as a hard rock geologist. And then I got into studying landscape evolution and discovered that that stuff that covered up the rocks, the soil, was actually really kind of important for shaping landscapes. And managed to study soil erosion around the world for a few decades, and really have gradually come to see this soil health movement as something that is really important, really critical, and really exciting. And I wrote this book, Dirt, the Erosion of Civilizations, up there on the left-hand side of the screen about 10 years ago now. And that's the kind of a book that you might expect a geologist to write about soil. It's very backwards looking. It looks back through history. It looks back at the most recent period of geologic time, the part that we've greatly shaped and influenced. And I struggled hard with how to write the last chapter of that book. And I'll give you a bit of a taste for that over the next few minutes. But it basically looks at defining the problem of what has been the problem with the way that people have treated land over the centuries and the problems that soil erosion and soil degradation have caused for human societies. That middle book, The Hidden Half of Nature, that I wrote with my wife, who's a biologist, was really our exploration of learning the role of microbes in soil fertility, the part that we weren't really taught when we were in graduate school, and how that opened our eyes to potential solutions to the problems identified in the Dirt book. And that third book, Growing a Revolution, is the most recent one, and that essentially was the story of me going around the world and listening to farmers who had already restored fertility to their land and trying to connect the dots between this long-term pattern of soil degradation, the new science that allows us to understand the role of microbes in soil fertility, and the practical applications of what does that mean for the world's farmlands. So, and if anyone's live tweeting, our handle is @dig2grow, as is up there on the screen. Encourage you to spread the word to people outside this room. But let me start, since I am an academic, with a pop quiz. Which planet would you rather live on? The one with air and water? And that third thing we often forget to mention, soil. Or that red one over there. I vote for Earth, and if you look at the nature of the soil on Mars, we're not going there to farm anytime soon. It's battery acid. It's going to be, despite what you may see in the movies, it would be really hard to generate an agricultural civilization on Mars. That confluence of a breathable atmosphere, freely abundant water, and healthy, fertile soil is really what has promoted life on this planet for a very long time, once life left the oceans and colonized the areas that we can actually inhabit quite readily. So this gives you a bit of a hint for why a geologist like me would be very concerned about the state of the world's soils. This map that's up there now is the UN's global map of soil degradation from a few years ago now. And you'll notice there's an awful lot of yellow and red zones on that map, areas where the land has been degraded in terms of its agricultural potential. I also want to point out that despite the kind of the ominous look of all that color on this map, you can go into each of those red zones on the map and find farms that are building soil fertility. They're absolutely turning around the picture you would take home from the broad pattern on this map. So in this talk, I'm going to try and take you on my own intellectual journey, going from somebody who looks at the broad picture of this map and goes, oh my, we're in trouble, to somebody who thinks, oh yeah, we can fix this. And why do I know that? Because I've visited farmers around the world who have already done it on their own land. That it's not a theory, that it could be done. But first, I'm going to spend probably about 10 minutes either depressing you or just reviewing things that you already know. Because there's a study in terms of the state of the world's soils. And there's a study that David Pimentel and his colleagues at Cornell did a few years back now that tried to tally up the magnitude of the soil degradation due to anthropogenic human influences on this planet over the time of the second half of the 20th century. And they basically wrote that some 430 million hectares of land had been abandoned between the Second World War and the end of the century around the world. That's an area, and that had been abandoned to agriculture. Once productive farmland that was no longer in agriculture. That's an awful lot of land. That's about a third of all cropland, and that's about an area the size of India and China combined. And if you really look at this in the way that I'm going to the next few minutes, this would actually be an underestimate because it's not including the land degradation that occurred in ancient times. And you can quibble a bit perhaps about their numbers or the trend, but it's a scary large amount of land around the world has been taken out of agricultural production because of the way that we have degraded it. And if you look at the most recent assessment of the state of the world's soils, one that came out in 2015 from the United Nations in their Global State of the Soil Assessment, you burrow into there and you read it and you find that they assess that humanity's losing about 0.3% of our global food production capacity each and every year to ongoing soil erosion and degradation. That's kind of a slow rate, right? 0.3%? Sound kind of like what we're all getting for our savings accounts? It's not a big number, but it adds up over time. If you take that number and you project it out another 100 years, we'd be on track, according to this report, to degrade about another third of our agricultural production capacity. And 100 years to a geologist is not a very long time. It may be absolutely forever or over forever's horizon in the political world. But in the geological world, that's round-off error on tomorrow morning. And so if we've already degraded something like a third of the world's cropland, and we're on track the way things are going to degrade another third in the next century, it's my contention that agriculture is going to need to change. And that's why I'm so excited about this idea of soil health, what Howard Buffett has called the Brown Revolution, a soil health revolution. There's lots of terms we could throw at it, but the fundamental idea under that idea, that vision of his, is really sound and I think really important for the future of humanity for these very simple reasons. We need to turn around the degradation of our agricultural land. And we have this century to do it. Maybe we only have even have a few decades. But as a geologist, I tend to be a little patient about those kind of things. But there is an urgent need to address this problem of ongoing soil degradation around the world and actually not just slow it down, but reverse it. And I wrote about the first part, that's sort of the pattern and history of ancient societies in that dirt book. And it was an exploration of going into the archaeological world, reading archaeological papers, visiting areas around the world where soil had been degraded, and really trying to put the story together of how the way people treated land affected the way the land would treat people over time. And I was actually trying to update a great book that was written by some Soil Conservation Service scientists back in the 1950s called Topsoil and Civilization. I don't know if anyone has read that book, but I read it as an undergraduate in college. I loved it. It convinced me that soil was something worthy of attention and interesting even to a geologist. And in trying to update that book, what I did is I looked at the role that soil erosion played in ancient societies. And it played a really major role in the demise of ancient civilizations, from Neolithic or Bronze Age Europe to classical Greece, Rome, the southern United States, Central America, and more that I cataloged in that book. And there was a problem, I realized, with the usual explanation that you find in environmental history textbooks, which is that deforestation led to the destruction of soil, to the erosion of soil that helped undermine ancient civilizations. And I've done a lot of work on soil erosion on the west coast of the US and in steep lands around the world. And I can assure you that clear-cutting steep slopes leads to accelerated soil erosion. but it does it in a very small portion of the landscape. There's very sensitive areas that you can identify. And the numbers simply don't pencil out in terms of erosion rates following timber harvest to explain the wholesale loss of soil that we've seen in ancient societies around the world. And I started to realize that there was actually a different culprit in the history of soil erosion and its effect on human civilizations, and it wasn't the axe that caused the erosion, it was the plow that followed. And so if there can be a villain in a non-fiction book, the villain of my dirt book was the plow. This was not what I expected to be learning when I started writing that book. I thought I was just going to read a fun bunch of archaeological things, maybe get to travel to some neat parts of the world, learn some ancient history. I came away realizing that I was writing a history of farming and essentially a case and argument for ditching the plow, for no-till farming. And why is it that the plow led to such accelerated soil erosion? Well, think about what a plow does. I mean, it's exceptionally good weed control, right? And it inverts the soil, takes out what's growing on the surface, but it also gives wind and rain a fresh surface to work on. And it also reduces soil structure, pulverizes the soil, a bunch of other things that soil scientists would love to argue and think about. But the way a geologist like myself thinks about it is that the plow essentially changed the relationship between soil erosion and soil production from one that was naturally in balance to one that was out of balance. How many of you ever gone out to a native grassland or forest around the world and seen a whole lot of bare earth? You don't. Nature clothes herself in plants. And there's this long relationship between vegetation and soil that you can trace right back to when plants came out of the sea and started colonizing land, and the organic matter that the plants built up built the quality of the soil up. That fertile soil helped plants grow, and we were off and running in terms of terrestrial ecosystems. The plow fundamentally alters that on the land that we have, in society after society, depended on to grow our food. And if there's one thing that I kind of know from economics, and especially from looking at my own personal finances, it's that if you use something up, if you spend faster than you replace it faster than you have income, you're burning up your savings. And at a societal level, the soil is our natural capital. It's our society's bank account. And soil erosion that proceeds faster than soil building is quite literally drawing down our natural supply of capital. And this has been a problem in societies around the world. I'm going to pick on my own home state of Washington for a minute simply to illustrate the point of why a geologist like myself would look at a picture like this of a winter wheat field in the Palouse in eastern Washington from back in 1970 and think that the soil is just absolutely bleeding off the landscape. All those little channels, those little rills that happened after the field was plowed, before the next crop came back in, and this I believe it was a winter wheat fallow rotation in this case, those little channels are kind of an agricultural nuisance. You can erase them with a single pass of the plow. But what happens if they come back each and every year? They really start to add up. And the second picture, also from the Palouse, illustrates the magnitude of that kind of effect. That fence up in the upper right-hand corner of the slide is a fence that the farmer built around their water cistern back in 1911 when the native grasses were first plowed to make way for a winter wheat fallow rotation, which is all that happened in this field for the next 50 years. And you'll notice that there's a bit of a cliff around that fence that is a result of those little rills each and every year coming in, and the action of the plow moving soil away from the fence line and downhill. What you can't really see terribly well on this negative is that there's actually a kind of a washed out survey rod in there, and there's a little black bit that, let's see if I can actually point to it, that goes from about there to there, that little black thing there. That's actually a 1 foot increment on a stadia rod, a survey rod. That cliff, in other words, is 5 feet tall. 5 feet of soil erosion in 50 years is about a foot a decade. That's about an inch of erosion every year. And I'll show you data in a minute that should convince you that, well, there's nowhere on earth that soils form at a pace of an inch a year, except perhaps in my wife's garden and perhaps on your farm, because we can actually form soils faster than nature does it. And that's something that was quite a revelation to me. But we'll get there. That's in the second book. And I'm still on the depressing part. So you should be sitting there thinking, Dave, isn't that a pretty extreme example? And of course it is. That's why I like to use it. How typical is it? And how could it be, and that was like one corner of one farm. What about whole regions? Well, I'm going to use one example. I have lots of regional and national examples in the Dirt Book, but I'm going to use the southeast of the United States, the Piedmont region, the upland hill country from Virginia up there in the upper right down to Alabama in the lower left, one of the original agricultural powerhouses and breadbaskets of the American colonies. And what I'm showing you in that gray noodle is the amount of topsoil that's been lost since colonial agriculture began. So, roughly 200 years, 250 or so of integrated soil loss. And you'll notice there's 4 to 10 inches, that gray stuff, around most of that region. And the black stuff is more than 10 inches of topsoil erosion. Well, how big a deal was that? If you go back and you actually read the journals of some of the original farmers that first worked this land, there's only about 6 to 12 inches of rich black earth in the forest soils that were first cleared for agriculture. In other words, we've eroded off anywhere from 1/3 to darn near all of the topsoil across a pretty wide swath of what was originally one of the big agricultural regions of this country. And that starts to put into perspective. We did it with just a 200-year run of the plow. That starts to put into perspective the idea that with a 1,000-year run at southern Greece, the ancient Greeks could quite literally plow the soil off their land. You can still find areas in the bare hill country of southern Greece where there's Bronze Age agricultural implements abandoned on areas that no longer have soil at all. It puts into perspective how the Romans could have plowed off the soils of central Italy with an 800-year run at central Italy. And how many of you have ever been to the ancient port of Rome, Ostia? It's nowhere near the coast. It's miles inland. Why? Because the soils of central Italy were washed down at a faster rate than they normally would, forming the famous Pontine Marshes and pushing the coastline out from where the port was. You can go stand on the old docks of Rome, and the sea is not visible. So it starts to put into perspective that the idea that agricultural soil loss and erosion maintained over generations could really add up to have major effects on human societies. And if you need to look no farther today than places like Syria and Libya to find places where the long-term legacy of soil degradation is still playing out to the detriment of the local population. You can go to Syria, for example, and find Roman tax records that document great harvests of wheat off land that's barely able to support a population today. Societies that destroy their soil take their own foundation out from underneath them. But there's also another change in soil that's not just related to soil erosion. This shows you pictures of 2 soils from North Carolina in that gray bubble on the previous slide that I showed you. And one of those soils is from a modern conventional tobacco field. It's actually off of a research station. The other one shows you the soil from the forest next door. Which would you rather be farming? One of them is basically beach sand with salt in it. The other one is soil that has a lot of organic matter, a lot of life in it. One of them is fertile. The other, its production is maintained by external inputs because its internal fertility has been depleted. Its soil organic matter has been depleted. There's farms that I visited in North Carolina where the topsoil is quite literally gone and people are farming the B horizon, the subsoil. And if you add enough inputs to it, you can coax a good crop out of it. But you're fundamentally hooked on and dependent on those inputs if you take out the natural fertility of the soil. And what have we done to the soil organic matter in the United States so far? We've depleted, by the estimates I've seen, roughly half of it. We've burned through about half our natural capital in a couple hundred years. Globally, it's about the same statistic. And you can argue about whether it's 50 or 70%. I've seen estimates even up to 80%, but I'm going to go with half. That's scary enough, and it's on the low end of estimates. So this really motivates the question of, well, how typical is this around the world? And in writing the Dirt Book, I did a lot of work looking at the archaeological story, but I also wanted to look at modern data to try and see if the numbers for modern studies that have actually documented soil loss and erosion and degradation off of fields, do they add up to enough to actually help explain the wholesale loss of soil off of regions around the world in the past? Because we didn't actually have, when I went back and researched Roman agricultural soil loss, there's only 4 books that survived about Roman agriculture. And they're kind of cryptic and vague. There weren't people there actually collecting data on sediment flux off of Roman fields. But we have that kind of data today. So I want to figure out, how do the numbers pencil out? So I went to the literature. I did something that was a bit unusual these days, I guess, and that is I didn't just sort of Google the first 10 like returns on soil erosion. I went to the library for about a month, and I dug up every scrap of data I could find in that period. And why did I only spend a month doing it? That's all the time I had. So here's what I found. I basically found 1,400 studies, and I published the results of this in the Proceedings of the National Academy of Sciences the same year the Dirt Book came out, back in 2007. If you want this kind of a data, or you want to see what's behind it, go look that paper up. There's an Excel spreadsheet online. You can take it, steal it. Nobody should ever have to do this exercise again and compile this data again. So what I'm showing you are the measurement types on the left-hand side and the median, or the average value, on the right-hand side. And a median is that kind of average for half or smaller, half or bigger. So it's just the middle rank number. And the numbers in parentheses after the labels on the left, that's how many peer-reviewed academic studies I used to generate that average. So, in other words, I did a fair amount of homework. Is it comprehensive? No. There's a lot more data one could pull into something like this. But I at least did due diligence on it. That number at the top is the bad news number. That's the erosion rate off of conventionally plowed fields as a global average. So it's everything from subsistence farming that uses a plow right on up to modern mechanized stuff at large scale in North America. And you'll notice that it's about 1.5 millimeters a year is the globally averaged erosion rate off of conventionally plowed fields. Now, 1.5 millimeters a year sounds pretty slow. Your fingernails grow 10 times faster than that. The San Andreas Fault moves 40 times faster than that, and I've never seen it move. And hopefully it won't. But it's a scary big number to a geologist. Why? Because of those blue numbers at the bottom. Those are the erosion rates under native vegetation, globally averaged. So these are thick, fuzzy glasses of a geologist. They don't apply in any particular farm. They're just the global average. But erosion rates under native vegetation, rates that soils are produced naturally, and long-term geological erosion rates are all about the same. 1% or 2 of a millimeter a year. That's like 20 to 100 times slower than our rate of agricultural soil loss off of conventionally plowed fields. And those USDA T values, I don't believe them for a minute. They're kind of meaningless. The good news number is that number for no-till, agriculture that doesn't involve the plow. I've colored it blue because it's really a lot closer to those numbers at the bottom. We can essentially, I think we know how to solve the soil erosion problem. It's to stop plowing. It's to go to no-till practices. And that's sort of the foundation for agricultural sustainability, is don't lose the soil. And foregoing the plow is a way to actually do that. You can also run in your mind's eye the sort of experiment, or on the back of a napkin if you want, what the data that I've just shown you means for the hypothesis that I was looking at in the Dirt Book of could agricultural loss and degradation take out ancient societies? Could that have been one of the causes, one of the contributing factors to the demise of societies? So if we take that net soil loss of about 1 millimeter a year, and recall I had about 1.5 millimeters that I showed you as the average. Let's go conservative. We'll go for just 1 millimeter a year difference between those numbers. It implies that you could erode a 1 to 3 foot thick or a 0.5 meter to meter thick soil in about 500 to 1,000 years, which again, to a geologist is really fast. To a society, that's kind of slow. That's generations. It's hard to notice over one lifetime, but it adds up over just a few generations. And that time frame, that sort of 1,000-year-ish kind of time frame, is it's approximately the lifespan of most major agricultural civilizations, with some really key important exceptions. Those are the major river floodplains of the world. Places like the Nile, the Tigris and Euphrates, the Indus and the Brahmaputra in India, the rivers of lowland China in Asia. Those are places where agricultural societies have been able to maintain tillage-based agriculture for thousands of years for a simple reason. They're floodplains. They get fresh soil delivered every year to their door by rising waters, as long as you don't dike the rivers off and prevent floods from happening, which got Mesopotamia into trouble and has caused trouble agriculturally in other regions of the world, but it's kind of beside the point I want to make here. What I want to do is draw your attention to the regions in the headwaters of those long-lived societies, Because these are areas where soil erosion has actually crippled societies over time. Places like Syria in the headwaters of the Tigris and Euphrates, Somalia and Ethiopia in the headwaters of the Nile, the Himalaya in the headwaters of the big rivers in India, or the eastern edge of the Tibetan Plateau, which was the original seat of Chinese agriculture and was abandoned centuries ago due to soil loss and degradation as people moved down onto the regularly fertilized floodplains. So the problems that those societies have had over the long run kind of help illustrate that soil loss and erosion in the headwaters of those systems was subsidizing civilizations down on the river floodplains. So that's kind of the end of the really depressing part of the talk. Because I started grappling with the question of whether soil restoration is possible and whether we could reverse this historical pattern. And that's something that I started grappling with really in writing the last chapter of the Dirt book, because what you will read in that book is my third attempt to write that last chapter. The first two attempts were I deemed too depressing to actually put into print, and I went back and went, okay, what can I think about here that might be a little more optimistic? Well, at the same time that I was writing that, I was starting to learn about the transformative potential of thinking about the soil differently, and particularly about thinking about that part of life in the soil that we don't see with our own senses, that's out of sight, out of mind, below ground, and out of touch with our own senses, the microbial world. And I wrote about that with my co-author and wife, Anne Buckley, who's a biologist, in The Hidden Half of Nature. And if you think about what makes healthy, fertile soil in the way we now know and understand it, it's the marriage of geology and biology. And we happened to have that going on in our own house, and we figured, and through observation and accident, because we weren't intending to figure this story out, we were trying to make a garden. In part because Anne is a gardener, and as a biologist who studied plants, this is sort of her world. I think of her as a plant whisperer. I'm that guy in the office that if you give a house plant to, it'll be dead in a month because I forget to water it and stuff. And this is what, you don't give a geologist a plant to care for. But Anne is really quite incredible with plants. And we bought this house in North Seattle back in the late 1990s. When I got tenure at the University of Washington, we decided that Seattle was actually a pretty nice place after all, and we would stay there. We bought a house. It had a lawn as sort of a side lawn that I'm showing you here. And note the neighbor's place in the back. It'll come up a little later. But also note this. When we peeled that lawn off, that we had this really sort of rich, fertile black earth that North Seattle's known for. No, we had glacial till. We had really crap soil. And we had dirt, basically. There was no life in it. We didn't have a single worm. There was no macroscopic life forms. We didn't see anything living in that soil when we peeled that lawn off. And we kind of went, oh, should have dug a soil pit. Didn't think to do that when I was shopping for a house. Done that all over the world for research. Didn't think to do it at home. We realized we had a problem. We had dirt, we wanted soil, and wanted to grow a garden. This was not the stuff that was really going to help. And so she took it on herself to really start what in the book we termed her organic matter crusade, because she realized we had the geological half of good soil. We had a whole lot of ground up pieces of British Columbia that had been bulldozed by a great ice sheet, dumped down in Seattle and then overridden by a mile-high wall of ice that's about 3 times the height of the Space Needle that compressed it into nature's concrete. We had the raw stuff. They had the raw mineral matter for good soil. We didn't have the biology. We were lacking the life. So she started raking up our neighbors' oak leaves in the fall. You'd be surprised how welcoming and nice neighbors are in the city when you come over with your wheelbarrow and rake up their leaves and take them away. They didn't realize that they were just like giving us stuff to fertilize our yard, and they were undermining the fertility of their own land. The Seattle Zoo has a program where they give away what's called Zoo Doo, which is exactly what you think it might be. It's the composted turds from the herbivores. And they have a lottery, and we kept entering it, and I had a pickup truck, and so Anne would load my truck up with Zoo Doo, and we kept thinking, wow, we won again, this is great. And I think the reality is that you always win the Zoo Doo lottery. So we basically were adding organic matter wherever we could get it. And we started off with thinking that we just wanted to like mulch the soil to keep water in it because even in Seattle, you have to water sometimes. We first planted in August. We had a bunch of little plants. Anyway, we kept going with this soil composting and mulching regimen for a couple years, and we started to notice within about 3 years that our soil was getting darker. It had gone from that khaki beach color to a sort of a milk chocolatey. And this shows you the soil pit that I probably should have dug when I bought the house, but I dug this about 3 to 4 years after we had started the yard transformation. And you can see the leaves and the wood chips, the mulch that we put on the surface, and down at the bottom you can see we still have glacial till. We didn't dig anything up, we didn't rototill. We just kept adding organic matter to the surface, and we would find that it would basically decay, it would disappear over the course of 3 to 6 months. We'd have to go scrounge and add more. And once we saw the color of the yard changing, the colors of the soil changing, we decided, okay, we'll dig a pit, what do we have? And you'll notice that Ann's pruning shears are there, and in between that, the surface compost and mulch and the till at depth, we've got about 2 inches of halfway decent soil in just a couple years. This is beating nature at her own game in terms of pace of soil formation. And to be fair, a geologist tends to think of building soil by breaking rocks up, but you can also do it by adding organic matter to already pulverized mineral matter. And that's what we had in our yard, and that's what we have on many farms around the world. We already have some soil, we're not just farming rock. The challenge is to get the biology back, to get the organic matter back, to bring soil back to life, the subtitle of the new book. And so here we've got about 2 inches of soil built in about 5 years. That's going to be about 4 inches a decade. That's more than a meter in a century. You look at the global average soil depth in the UN Global Soil Database, it's less than a meter. It's about 75 centimeters. It's about 2 feet, 2.5 feet. If you could rebuild soil at a global average kind of perspective in the course of a century, that's remarkably fast. And I'm not saying we could do that all around the world, but I am saying we can do what we have up here on the screen now. This is what we did in our yard. In my right hand, the one on the left side of the screen there is the soil that we started with in our yard. It had less than 0.5% organic matter. The soil in my right hand, it's the same dirt, same soil. It's just about 15 years later with the composting and mulching and organic matter additions that we had in our yard, and it's up to about 8 to 10% organic matter. We've stored about 8 tons, for those who do carbon accounting, we've spent about 8 tons or so of carbon in our yard through our gardening practices. And we did it basically to try and do this, to make a garden. And having a nice garden in our yard has transformed our lives, the way we use the yard. We live outside now basically in the summer where there's late nights in Seattle and so forth. I won't bore you with the details of that, but I do want to point out the neighbor's house back there, we don't see it anymore. They're lovely people, but I got tired of watching their kids grow up. Much nicer to live in a city with a wall of green between you and the neighbors, but we don't have to dwell on that. The other thing that I learned, that Ann and I both learned, and that really woke us up to what was really going on here, was that sort of the stars of this transformation of our soil weren't Ann and I. We were kind of helping to facilitate it, but we weren't doing the really heavy lifting on it. That was going on below ground. That was being done by microbes. That was being done in the microbial world. And one of the things we learned in starting to look into, because we're both scientists, right? So we see this transformation in our yard, we see our organic matter disappearing, we go, what's going on here? So we dig into it, and we realize that there's this zone around the root zone of a plant, it's called the rhizosphere, that is one of the most life-rich zones on the planet. You want to go find a whole lot of microbes, dig around the root zone of a healthy plant. They're surrounded by microorganisms, much more so than at distance from roots. And a big part of what's going on there is something that our eyes were open to in researching this book, and that is that what we were taught in terms of what plant roots do was only half the story. Because we learned that plant roots are essentially straws that help facilitate acquisition of nutrients from the soil. But they also push stuff out into the soil, things called exudates, which many of you have probably heard of, and which consist of things like sugars, carbohydrates. Plants have a monopoly on being able to turn carbon dioxide and water into carbohydrates, and they have this wonderful side effect of pushing oxygen into the atmosphere, which we all appreciate. But they also build a botanical world that way. They have a monopoly on being able to do that. But they will push out up to about 30 to 40% some plants, 30 to 40% of the material they build through photosynthesis, they'll push it out of their roots into the soil as exudates. They exude it into the soil. And what are those materials? It's the carbohydrates, the sugars that I mentioned. It's also proteins. They'll do hormones. But last year, there was a paper that came out where people documented plants pushing fats, lipids, out into the soil. What are carbohydrates, proteins, and fats? That's food, lunch, breakfast, dinner. It's food, basically. Plants are pushing food out into the soil, and they're not doing it simply because they have too much food. They're doing it to feed those microbes in the soil. Those microbes, the reason that the rhizosphere is such a life-dense zone is not because pests and pathogens are gathering to attack plants. They're gathering because the plants are setting a subterranean buffet for microbes. Now, why would plants do that? How many of us give away 30 to 40% of our annual income? Other than taxes, that is. Or maybe there is a good analogy there. Maybe the plants are taxing themselves to actually support this their microbial assistance out in the soil that couldn't survive without the food that they're getting from the plants. And the plants get something in return, kind of the way that we get roads to drive on and a military to protect us. There are some benefits from being taxed. We could argue about the level, but that's not what we're going to do today. But there's something that's going on in the rhizosphere is that there's a biological bazaar going on. There's interchanges and interactions between the microbial life in the soil and the plants. And this shows you sort of a blow-up of what Ann and I have turned the biological bazaar, where microbes and plants are trading nutrients, metabolites, and exudates. And in that center piece where you see that root coming down, with the blue thing is the rhizosphere, where you've got all kinds of bacterial and fungal life. The plants are pushing the exudates out into the soil, those black lines, and that stuff doesn't stick around very long. It gets consumed. It gets about 1 millimeter to 1 centimeter, about the thickness of my thumbnail to the length of my thumbnail, out away from roots into the soil before something eats it. And what happens to stuff that gets eaten? It gets metabolized. And what happens to the waste products of metabolism? An organism will excrete them. And so we have all these microbial metabolites coming back out into the root zone of plants, right around roots, because that's where they're living and things are being consumed. What are those kind of metabolites? When Ann and I learned that those include things like plant growth promoting hormones, we were astounded. Because here you have microbial life in the soil, bacteria in the soil, producing hormones to make plants grow and to keep plants healthy. Think about that. That's one sort of whole kingdom of life making fundamental compounds that would promote the health of a completely different kingdom of life. The only reason they're doing that is these are mutually beneficial exchanges, true symbioses, partnerships between life in the soil and the plants that are growing in it. And these partnerships go back to the very dawn of life on land, because the first plant fossils that we have examples of have mycorrhizal fungi intertwined with their roots. The fungi these partnerships helped plants come ashore and colonize the continents. Roots originally were simply structural supports. The fungi fed the plants. Roots evolved their behaviors that I was taught in graduate school later. These are very deep evolutionary partnerships. And when Ann and I realized the functionality that microbial ecosystems were providing to plants in terms of nutrient acquisition, in terms of teeing up their defensive systems, in terms of chemical signaling, all mediated through these partnerships and exchanges in the rhizosphere, we're like, wow, this is kind of how nature works. When we realized that the human gut works the same way, just inside out, that's when we wrote The Hidden Half of Nature, because this really is fundamental to understanding what creates the health and nutrition of not only our plants, but our own bodies. And I'm not going to talk about the human colon today. You can read the book if you want to get into that. But the parallels with what's happening in the root zone of plants are actually striking. And what does this mean for how we think about plants? Well, we need to think about them having a diet. And if you think about what these partnerships mean, if you have a plant that's growing in a organic matter and nutrient poor soil, you can support it, you can grow it on a fertilizer diet. You can feed it the NPK that it needs, you can feed it a lot of it, and you can grow big plants. You can get big yields. We all know this. And in fact, if you have degraded soil, that's one of the reasons that intensive agrochemical use became very central to modern agriculture in the 20th century. We had already degraded our soil organic matter and fertility of lands in the developed world. But what does that do to the plants? Plants don't put out as extensive a root system if they're getting most of the macronutrients they need. Ann and I term that behavior couch potato crops. They get kind of lazy. They don't put out the root system, the same root system. That means they're not putting out as many exudates. That means they're not recruiting as many, they're not exerting the same selective pressure on the soil life, so they're not getting the same composition of beneficial organisms in the soil as they would if they were growing in a very organic matter-rich soil, what Ann and I term here the soil health diet, which you can still fertilize them if you're basically need to add NPK to it, but by having a healthy, fertile soil, you're getting more in the way of the micronutrients that the fungi will provision for the plants, and you're getting more of those beneficial microbial metabolites that promote the health of the plants. So here we have a fairly simple explanation, perhaps, for why the global demand for pesticides went through the roof as the global use of fertilizers went through the roof. We disarmed the defensive systems of our plants. And that's not to slam fertilizers, but it's to basically argue that we need to think about the way that plants eat and defend themselves and nourish themselves, what makes plants healthy, because the connection between healthy soil and healthy plants is actually now pretty clean and pretty clear in terms of the academic literature. And so in thinking, as Ann and my eyes were open to this new way of sort of thinking about soils and soil health in our yard, we started to think about, well, how could these ideas apply around the world, to farms around the world? Could we basically apply these same kind of lessons to rebuild the health and fertility of the world's farmlands? And I started first thinking about this actually when I gave a talk at the World Conservation Agriculture Congress, I think in 2014, and Howard Buffett was one of the other speakers, speaking about his idea of a brown revolution. And that really inspired me and resonated with me about, wow, could we basically take these ideas? And as a geologist, I sort of figured this is a good excuse to do a little field work. And I never thought when I was in graduate school that field work would involve going around and visiting farms and asking farmers, how did you change your soil? What did you do? What are your practices? And let's take a shovel, let's dig a hole on your land and your neighbor's land and see what happened. And that's basically what I did, is I visited farms, took about 6 months off, visited farms around the world to basically ask these questions of farmers who had already rebuilt the health of their soil. What did they do? What were the principles behind what they did? And what I found was that farmers who had adopted the principles of conservation agriculture, which I'll define in a moment, that was the common element between farmers who had really radically improved their soil in remarkably short order. And that they could match conventional crop yields using far less oil and chemical inputs. And I visited one organic farm. I visited the Rodale Institute. But I mostly visited conventional farms because I wanted to see what the magnitude of the change could be there. So what are these principles? These three principles that worked across the board on the organic farms and on more conventional ones were not a secret. I didn't make these up. They're minimal or no disturbance, the direct planting of seeds or going no-till. There's maintaining a permanent ground cover, raising cover crops and retaining crop residues, and adopting more diverse rotations to help break up pathogen carryover. These three simple ideas were the common elements between the farms that, around the world that I visited that had radically improved their soil. And all those little microbes around there on the screen are meant to remind me to basically say that the reason that these practices work is this is a recipe here for cultivating beneficial soil life. Don't disturb it, don't break up those mycorrhizal fungi, feed it organic matter, feed it carbon, give it something to eat, and don't allow just one or two species an opportunity to really take advantage and attack something. If you plant corn in the same field year after year, you're inviting corn pests to dinner. What you want is a diverse community of life in the soil to help keep corn pests away from your plants. So anyway, these are basically the basic ideas that the principles that underlay the farms I found to be very successful. And many of you probably know David Brandt. He was one of the key people that I visited. He'll come back in a few minutes. But basically, some of the things that, well, let me actually go back to this list. Those bottom two, cover crops and crop rotations, those are not new ideas. Those are ancient ideas. You can find examples of that in societies around the world. Thomas Jefferson was all about cover crops and crop rotations, but he also invented that plow that still graces the seal of the USDA for some reason. Oh, did I say that? Jefferson was brilliant, right? He also invented a plow that could contour plow. Fabulous invention. But what's really unique about combining these three elements together in a new system of farming is taking that ancient wisdom of crop rotations and cover crops and getting it to work with the modern technologies that allow us to do minimal disturbance or no-till. You know, things from the herbicides that we have to cover crops and the kind of thing that I'll show you from Rodale in a moment, to sort of more ecologically managing weed suppression, getting modern science and ancient wisdom to work to align to implement these three principles is really the key thing. And so part of that are new technologies like this, like David Brandt, the no-till planter that Brandt is showing off here. And the thing that I found so interesting about this is the right-hand side of the screen is a freshly planted field. Now compare that in your mind's eye to what I was showing you from eastern Washington in terms of, you know, freshly plowed fields. There's no bare soil. You can barely even tell the ground was disturbed. That's a sea change in thinking about how we prepare the ground for planting and for soil. And it can radically, basically cut erosion off at the knees. If we think in terms of managing cover crops, Jeff Moyer, who's here but did me the favor of modeling his roller crimper here out of the Rodale Institute when I was researching the book. You know, there's new ways of thinking about how to actually generate weed suppression rather than using a plow. So there's new ways of thinking, new technologies that we can combine with different ways of thinking about how to treat the soil, how to sequence things. And I'll show you a series of, I think, 4 farmers that were very influential in my own thinking. Dwayne Beck here from Dakota Lakes Research Farm was instrumental. He was the first farm that I actually visited, and that was practicing, you know, cover crops along with no-till. And why did I go visit Dwayne? He was also I think at the 2014 conference. I saw him give a talk either there or at another one and was like, I got to visit this guy's farm if I write that book. He's doing very interesting stuff. He was kind enough to give me 3 days of his time, took me on a several hundred-mile driving tour around his neighborhood around Pierre, South Dakota, which, not coincidentally, is the area that I showed on the cover of the Dirt book, in the heart of the Dust Bowl. I saw only a couple plowed fields in an all-day drive, which is the point he wanted to make. This region has been transformed in terms of going to no-till. The black soil doesn't blow every time the wind comes up anymore. That is a major change. And what happened in terms of their agronomic practices? By adopting no-till cover crops and complex rotations, that, you know, gradually over time and experimenting with it, they were able to greatly reduce their uses of diesel, fertilizer, and pesticide by more than half in most cases. And that really impressed me because basically they'd figured out a way to grow just as much by using less. And you'll notice what happened to their yields. So all their inputs went down. That saved farmers money. They were also able to farm whole farms rather than having a wheat fallow rotation. They were able to actually grow something on all their land every year, which is a major productivity boost. But even in the traditional sense, their yields went up. You can check out their soybean and corn yields in this one example that I pulled from my notes on one of his test plots. If you can spend less to grow more, that translates very directly. Even a geologist can tell you that that translates into better on-farm economics. And don't take investment advice from me. But even I can recognize a good opportunity. So when I left Beck's farm, I basically asked him, well, you know, this is pretty impressive. We'd visited some to like, what, 20,000 acre farms, if I recall, Dan, that, you know, some large operations. I asked Dwayne, how big, you know, could these ideas translate to small subsistence farms in the developing world, in Africa, say? Because that's where really the problem of feeding the world lies for the next century, is how to feed Africa. And the population is expected to grow there. And he said, you know, don't ask me, go talk to Kofi Boa. He's already done it. So I got in a plane, went to Ghana, in equatorial West Africa, to ask this gentleman here who has this wonderful Got Dirt, Get Soil hat, which I got out of the car. First thing I see about him, I was like, I like this guy. He's like on the right track. And he has a farm that is basically practicing diversity in terms of what's being grown on the site at one time. Very small farms, the individual farms are smaller than this room that we're in, and they're mostly subsistence farmers that he's working with who don't have the resources to buy a lot of fertilizer or a lot of pesticide or a lot of agricultural implements. They mostly have their own labor to work with. And what he's been able to do is by getting them to, you'll notice that on the fields there's multiple crops, there's plantains, there's peppers, and there's other things growing in that field. What you don't see is bare earth. What Kofi's been able to do at the No-Till Center in Kumasi is to transform the practices of the farmers in his region from their traditional slash and burn practices, which once they ran out of new land to clear and they were slashing and burning on the same land over and over, that's a recipe for degrading your soil and your soil organic matter over time. Slash and burn only works if you can walk away, farm for a few years and then walk away for a few decades and let nature fix the land. But by adopting these practices of no-till with cover crops instead, they were able to curtail erosion. You'll notice their erosion rate went down by a factor of about 20 there. But look what happened to their yields. Their corn yield tripled, their cowpea yield doubled. That's as good a boost to production as was achieved in the Green Revolution, but this was done with no inputs, no additional cost. This was done with the change in thinking. This was done with applying the principles of conservation agriculture. And this was actually one of the first places that I saw that the demonstration of applying water to fields that were treated in different ways and looking at what runs off and what sinks in. They had a very nice example of that there. So the third farmer that I'll share, again, you all probably are familiar with David Brandt and his farm in Carroll, Ohio. I like to show this to audiences that are not farming audiences because people will look at that daikon radish and think farmer's market. But no, David is a commodity corn and soy grower. He grows a lot of other stuff on his farm, but he's selling corn and soybeans. But he's growing things like that daikon radish that would sell for an unspeakable amount at the farmer's market in Seattle. But David grows that to feed the microbes in his soil. He kind of considers himself a bit of a microbe rancher, I think. And he walked me through the example of what he's done in his farm, where he's gone no-till for 44 years, ever since he came back from a stint in the Marine Corps in Vietnam. And he's then adopted cover crops and has been diversifying his rotation. His field there behind me has a mix of 10 or so different cover crops in it that he pulled that radish out for me. But I also want to point out the field across the road, his neighbor's field behind him. It's kind of yellow. It's kind of a sickly soybeans at the time I took the picture. But the green stuff in that field are glyphosate-resistant weeds. They cover up to about 25% of many of his neighbor's fields by my visual estimation. That's a direct hit on their yields. David doesn't have any weeds. Didn't see a single weed on his farm. Saw an awful lot of cover crops though. He plants weeds, he grows weeds, and he kills them before they go to seed. He calls them cover crops. He's using them to get mineral elements out of the soil, the subsoil, into his topsoil, so he can kill the cover crop, so the nutrition that they've derived from the soil will go back into the topsoil and essentially fertilize his cash crop. So he ran me through the economics of his and his neighbor's operations, and this is where I really started to become a bit of an optimist that these kind of ideas could take on because, well, let's walk through the numbers. His neighbors are doing full tillage, 200 pounds of N per acre, 2.5 quarts of Roundup per acre. The total cost, he estimated about $500 an acre. The county average yield was on the order of 100 bushels an acre, according to David, the year that this, which I think was 2015. And at $4 a bushel, that means his neighbors were losing $100 an acre. That's a great business model, eh? I found a paper when I was, because what you do as an academic is you trust but verify. You sort of like get stories and then you go out and go, what are the academic papers that might back this up? There's a paper that came out that showed that farmers in Iowa, in 2015, I believe it was, that 25% of them lost money on every acre they planted. Think about that. If you can basically have farmers armed with some of the best technology in the world and some of the best farmland in the world that are hardworking people, and the more they work, the more money they lose, something is fundamentally wrong with our agricultural system. Well, let's compare that to the economics of David's farm. 44 years of no-till with cover crops. He's not tilling at all, so he saves on diesel. He's using 24 pounds of nitrogen an acre. He's not an organic farmer. He'd probably hit you if you called him an organic farmer. But I started teasing him that he was an organic-ish farmer because he's hardly using any fertilizer and he's hardly using any glyphosate. 1 quart per acre, about 1/5 of what his neighbors are using. So he's just not using as many inputs. And his total costs are a lot lower, therefore. He spent about $320 an acre that year. His yield was well above the county average, and it resulted in about at a $4 bushel price, he was making $400 an acre. It's a $500 an acre difference between he and his neighbors. That's huge. That's what started to turn me into a bit of an optimist. Not that these numbers would play out on every other farm, but simply the idea that there are demonstrated systems now where farmers can actually maintain, if not boost their yields at greatly reduced cost. And the biggest cost is changing how they're thinking about the land, how they're thinking about the soil, the nature of their practices, how they're approaching the problem. Gabe Brown's the last farmer that I'll talk about. He's gotten a lot of press in the last few years, in part because he's done amazing stuff on his land. And he's a wonderful, charismatic individual as well. And he's actually reintegrating livestock into his cropping operations and using cattle as a tool of soil rebuilding, which, as a geologist who'd studied gully formation in Northern California, I was trained to think, in fact, I did PhD work on those gullies, demonstrated that it was grazing operations in the late 19th century that triggered all those deep gullies north of San Francisco. If you ever go out in the Marin Headlands, it was, between 1880 and 1900. That's when they formed. In my mind, cows were bad. Cows equaled erosion. I was wrong. Gabe is the person who really convinced me by showing me how he had used livestock as a tool of soil regeneration. The problem wasn't the cows. The problem was how people were grazing in Marin County in the 19th century. It was how we were managing the livestock. And that makes sense when you think about what built the native grasslands of the Great Plains. The buffalo had something to do with it. And so Gabe basically was doing very innovative things of using his livestock to graze off his cover crops. So, if you think about weed control, there's herbicides, there's roller crimpers, and there's also cows. Why? Because they can eat them. They could eat the cover crops, they could eat weeds pretty happily too. So he was bringing his cattle into his market garden area, bringing chickens in to then help manage the flies by eating stuff out of the cow exudates. Did I just invent a term? But what I was really impressed by was what you can see with a shovel, which Gabe called the most important tool on a farm, and I think he's absolutely right, because this shows you his soil in one of his hands and the soil from his neighbor's organic farm in his other hand. And the organic farm is not that rich, deep, black one in this case. That's Gabe's farm. He's not an organic farmer. He's another one of these, what I call organic-ish farmers, just not using much in the way of inputs. And so why the difference between his farm and his neighbor's organic farm? His neighbor's organic farm uses a lot of tillage. They still use the plow. Gabe was able to build his organic matter up to probably higher than the native soil over a period of years through his different management practices. And I think he's using his livestock to accelerate the turnover and the breakdown of his cover crops and the reintegration of those nutrients back into the soil. He's feeding the microbial life in the soil. So what's the recipe that I can draw from all these lessons around the world? And I visited a bunch of other farms I describe in Growing a Revolution as well, but I basically boiled it down to three simple things: ditch the plow, cover up, and grow diversity. And those are basically the principles of conservation agriculture as the UN FAO has defined them. And you can add livestock to the mix if you want as well. I don't think that you have to do that to restore your soil, but I think it can be of great value and an accelerator if done right and properly managed. And if you think about these three principles and relate them to the principles that have guided modern conventional agriculture for the last 80 years or so, this is 180 degrees on all 3 points, because we've essentially institutionalized at a global scale intensive tillage, intensive chemical use, and growing 1 or 2 crops, functional monocultures. You just go down that list, and this is the opposite in terms of philosophy, which is not to say that one couldn't plow every now and then, or one couldn't use any agrochemicals, but it's basically a way of thinking. There's a different way as our frontline set of thinking to approach each of these problems, the problems behind these, how you nourish the soil, how you manage weeds, and how you deal with pests. This recipe really seemed to work, and to restore fertility to the land and productivity to farms. It allowed, in the examples that I drew on for the book, comparable, if not increased yields. This is not a question of the environment versus feeding the world. We can grow just as much, if not more, by adopting these principles. It resulted in reduced fossil fuel, fertilizer, and pesticide use. It didn't eliminate other than on the organic farm that I visited. It didn't eliminate these things, but in all cases it resulted in higher farmer profits, and these principles applied both and worked with both on organic and conventional farms. And they increased soil carbon content. All the color differences in the soils that I showed you, anything that went from khaki to dark brown or black, the difference is carbon, soil organic matter. They also result in better water retention, less off-site pollution, a whole host of benefits. And I want to emphasize that this is not really a question of organic versus conventional. This suite of practices can apply in both realms of agriculture. And I think if we can move the conventional agricultural world closer to what I term organic-ish by reducing the reliance on inputs, that is what could literally change farming and change the world and have lots of add-ons. There's still going to be room, I think, for both styles of agriculture into the future, but what we need to think about is how to apply an understanding of soil ecology to rebuilding soil health to sustain, if not increase, crop yields using far less inputs. Why would we want to, well, what would that do to agriculture? It would amount to another agricultural revolution. So if you'll indulge me for the last minute or two of what I want to leave you with, I want to basically try and explain to you why I think these practices could amount to a fifth agricultural revolution. So what were the first four? First one was agriculture, the whole idea of cultivating and tilling the earth. That was a revolution in the way that people treated the land, and it set the stage for the rise of complex civilizations in different places around the world. The idea that we could stay put and live in an area and support more of us was a radical idea. It was incredibly successful, and here we are. The second agricultural revolution happened in different places around the world, and it was realizing that taking care of the soil husbandry was actually important. Planting legumes in our crop rotations seemed to work. We didn't realize about the deal with nitrogen-fixing bacteria to the 19th century, but the idea of putting legumes in crop rotations was adopted by societies around the world long before that. The idea of rotating crops, cover crops, these are ancient ideas. And that quote from Leonardo da Vinci that's up there on the screen now, we know more about the movement of celestial bodies than about the soil underfoot. How many quotes from science 500 years ago, as this one is, are as current today as they were when first offered? We're just now learning the secrets of the soil, as NRCS puts it. I mean, our understanding of the role of microbial community ecology in promoting the health and growth of plants above ground has developed radically over the last few decades. And our understanding of our microbiome, the human microbiome, and the parallels with that is really brand new. There's a lot of stuff that we're just learning about the soil still. The third agricultural revolution was mechanization and industrialization in the 19th and early 20th century that greatly increased the amount of acreage under cultivation and a productivity of that land. Also caused a lot of soil erosion, but we'll skip over that for today. The fourth revolution, I lumped the green revolution and biotechnology into sort of a late 20th century technological revolution that really helped transform many aspects of agriculture. I don't want to go into the details on that, but what I want to basically point out is I think we're on the verge of what I like to think of as a fifth agricultural revolution, and that would be a soil health revolution, what Howard Buffett's called his brown revolution. And I think that this idea could be fundamentally transformative, not just to agriculture, but to human civilization. And why do I say that? I go back to the first book, the Dirt Book. If we don't get it right this time around, with our global civilization in terms of how we treat the land, we don't have anywhere else to go to. We simply have to get it right this time. And the problem of feeding a 9, 10, 11 billion person world isn't just the next 20, 30 years. It's not just a problem of feeding everybody in 2050. It's a problem of feeding everybody from 2050 on. And that we have to, the farming practices that we have today that are termed conventional are simply not sustainable over the long run. I think that the kind of practices that farmers demonstrated to me around the world and taught me about that would form the foundation of the soil health revolution, these new principles, those could actually be sustainable by maintaining the fertility of our land and building it as a consequence of intensive agriculture, what we could call a regenerative agriculture. That would be transformative. It would be a key moment in human history in our relationship, not only with the land, but with this planet. That's how we could become stewards of this world in ways that would allow us to persist. There's other benefits that we'd get as well. We could restore farm profitability over the short run, I think. It would help us feed the world over the long run. It could help us put carbon in the ground, which will help with climate change. And will also help with on and off-site pollution from farming activities and environmental degradation. If we look at the future of biodiversity on this planet, it's going to depend on what we do on farms, because a quarter to a third of the world's land mass is in agricultural production. However you look at whatever we're going to share this planet with, for the long run, is going to reflect what we do on farms. So I don't think that the soil health revolution and adopting these practices globally in terms of farmland will solve, it's not the magic bullet that will solve all of these problems, but it is something that will help address each and every one of them. And I'm hard-pressed to think of another single solution that one could offer that would have this many side benefits, when it actually looks like adopting these soil health building practices actually even today will pay for themselves in the current economy. So we're not talking environment versus the economy, we're talking real win-win-win here. And I've probably burned up my time, so I'm going to stop there. I brought copies. If people are interested in the books, there'll be books downstairs on the breaks. Come by and see me if you want to talk. Happy to do that. And Ann and I joined the social media world, so that's up there as well. But in any case, I thank you for your attention and for the good work that you're doing in trying to help rebuild fertility of the world's farmland. So thank you very much.